In 1926, a French inventor quietly patented a device that seemed to defy everything we understand about agriculture. No chemicals, no machines, no fuel, just a simple copper wire designed to capture energy from the sky. According to early reports, the results were almost unbelievable. Corn growing over 10 feet tall, pumpkins swelling to unnatural sizes, crops that didn't just survive, but thrived beyond expectation. Photographs circulated. Agricultural journals took notice. Even a British government committee began collecting evidence, trying to separate fact from exaggeration. And yet, almost as quickly as it appeared, the technology vanished. No widespread adoption, no continued research, no place in modern farming. It was as if the idea had been quietly erased. For over a century, we've been told that bigger harvests require more input, more fertilizer, more chemicals, more intervention. That productivity must be purchased season after season. But what if that assumption is wrong? What if somewhere along the way we traded a natural law for a business model? This is the story of a forgotten invention, a hidden force flowing through every field on Earth, and the question that still hasn't been fully answered. What if plants were never meant to grow alone? Long before industrial agriculture reshaped the way we grow food, one man was quietly challenging its foundations. His name was Justin Christofleau. He wasn't a university professor or a celebrated scientist. He was a farmer, an experimenter, the kind of person who trusted observation more than theory and results more than reputation. Born in France in 1865, Christoff spent decades studying something most people never even considered: the invisible energy surrounding every living thing. While others focused on soil chemistry, he asked a different question. What if plants don't just feed from the ground, but from the sky? This idea became an obsession. Over the years, he built a series of unusual devices: metal rods, copper wires, spirals, and antenna-like structures, placing them directly into the soil. His goal wasn't to add anything artificial, but to enhance what was already there. Then, in 1925, he took a bold step. Christoff filed a patent in Switzerland for what he called an electromagnetic atmospheric apparatus, a system designed to capture electrical energy from the air and channel it into the earth. The patent CH118648A was officially granted the following year. And it wasn't vague. It detailed every component: copper conductors, magnetic steel plates, specific configurations to guide energy into the soil. This wasn't a theory scribbled in a notebook. It was a complete testable system. But what truly drew attention were the results he claimed. He reported oats growing over 5 feet tall, trees that had stopped producing suddenly returning to life, harvests that seemed to break the limits of traditional farming. Instead of keeping it secret, Christoff published his findings in books and agricultural journals. He invited others to visit, to observe, to verify. For him, proof wasn't meant to be hidden. It was meant to grow right there in the field for anyone willing to look. By the mid-1920s, something unusual was happening across parts of Europe. Photographs began to circulate images that didn't look like ordinary agriculture. Pumpkins the size of barrels, cabbages nearly as tall as a person, fields producing harvests that seemed exaggerated, almost unreal. These weren't just rumors whispered between farmers. They appeared in gardening magazines, local newspapers, and promotional pamphlets tied to Christoff's work. To some, it looked like a breakthrough. To others, it looked like a carefully staged illusion. The images alone weren't enough. So attention turned toward verification. In 1918, the British government had already established a research body known as the British Electroculture Committee under the Ministry of Agriculture. Their mission was straightforward: investigate electroculture and determine whether it was science or speculation. By the early 1920s, the committee began collecting reports from across Europe. They gathered field photographs, crop yield records, testimonies from inventors and farmers, including those connected to Christofleau. Over nearly 2 decades, their archives grew filled with strange devices, unusual harvests, and repeated claims of increased productivity. But something didn't add up. Despite the volume of material, key pieces of evidence were missing. No original photographic negatives, no consistent third-party replication, no large-scale controlled validation. The results looked convincing, but never fully conclusive. Again and again, the same pattern appeared: strong claims, compelling images, lingering doubt. It left researchers in an uncomfortable position. Was this a real agricultural breakthrough, or a phenomenon that only worked under unclear conditions? The visual record demanded an explanation. But without solid proof, the line between discovery and legend began to blur. And the deeper scientists looked, the more one question remained. If this really worked, why wasn't it everywhere? Every field on Earth, whether it's a backyard garden or a vast stretch of farmland, sits beneath something we cannot see. An invisible flow of energy. It's not lightning. It's not something you can feel. But it's always there. Scientists call it the atmospheric potential gradient, a natural electrical difference between the sky above and the ground below. On a clear day, the air just above your head carries a positive charge. The soil beneath your feet holds a negative one, and between them, a constant voltage difference of about 100 volts per meter. That means for every meter you move upward, the electrical potential increases quietly, steadily, without interruption. This isn't theory, it's measurable. It's been studied for over a century. Even in calm weather, with no storms in sight, the earth and sky are exchanging electrical charge like a slow, invisible current. Now here's where it gets interesting. Plants don't just exist in this field. They are part of it. Leaves and stems are covered in microscopic structures, tiny hairs, waxy surfaces that can interact with electrical charge in the air. Roots buried deep in the soil connect directly to the Earth's negative potential. In effect, every plant becomes a kind of living bridge between sky and ground, a natural antenna. This isn't just a metaphor. In controlled experiments, scientists have driven metal rods into the soil and measured faint electrical currents flowing between air and earth, proof that this invisible system is active constantly. For most of human history, this background energy went unnoticed. It was simply too subtle to matter, or so it seemed. But in the early 20th century, inventors like Christofleau began to look at this differently. They asked a simple but radical question. If plants are already connected to this electrical field, what happens if we enhance that connection? What if, instead of adding more nutrients to the soil, we improved the plant's ability to interact with the energy already surrounding it? That idea, quiet, almost overlooked, would become the foundation of everything that followed. What if plants weren't just passive organisms absorbing water, sunlight, and nutrients? What if they were electrical systems? Inside every plant, a constant stream of tiny electrical signals is moving quietly, continuously, and with purpose. These signals are known as action potentials and variation potentials. They're not random. They act as messengers, carrying information from one part of the plant to another, triggering changes in growth, defense, and metabolism. In a way, plants don't just grow, they communicate. For example, when a leaf is damaged by an insect or a cut, an electrical signal travels through the stem to distant parts of the plant. Within seconds, other leaves begin activating defensive responses. Chemicals are produced. Growth patterns shift. All of this without a brain. Researchers have measured these signals using ultra-sensitive electrodes, detecting tiny voltage changes, moving cell to cell. Even subtle external changes like light temperature or mechanical stress can influence this electrical activity. But here's the key point. Plants don't just generate electrical signals, they respond to them. Studies have shown that when plants are exposed to weak external electrical fields, even at levels barely detectable, something changes. Growth rates can increase, antioxidant production can rise. Genes related to stress resistance may become more active. It's not dramatic, it's not instant, but it's measurable. Which leads to a deeper realization: plants are not isolated from their environment. They are constantly interacting with it electrically. This is where the idea behind electroculture begins to make more sense. If a plant's internal systems already rely on electrical signaling, then introducing a structured external field, even a gentle one, could influence how those systems behave. Not by forcing growth, but by guiding it. Early experimenters didn't fully understand the biology, but they observed the effects. And they began to wonder, if plants are already wired to respond to electrical signals, could a simple tool like a piece of copper shaped the right way enhance that response? That question would lead to one of the most unusual ideas in agricultural history. By now, one idea is becoming clear. Plants are not passive. They are electrical systems constantly interacting with the environment around them. So the next question is obvious. If plants already respond to electrical signals, can we improve that signal? This is where the copper spiral comes in. At first glance, it looks simple. Just a piece of wire shaped into a coil and placed into the soil. But its function is more precise than it appears. Copper is one of the most conductive materials available, far more efficient than plant tissue. That means it can collect and transfer electrical charge much more effectively than leaves or stems. And the shape the spiral is not random. In physics, spirals and coils are often used as antennas. They gather energy from a wide area and concentrate it into a single point. From radio waves to electromagnetic fields, this geometry shows up again and again. Early electroculture pioneers believed the same principle could apply here. A copper spiral placed in the soil could act as a passive antenna, capturing the natural electrical gradient between sky and earth and directing it toward the plant's root system, not forcing energy into the plant, but enhancing what is already there. This is a critical distinction. Unlike modern agriculture, which often relies on adding external inputs, fertilizers, chemicals, stimulants, electroculture aimed to work with the system, not against it, to amplify natural processes rather than replace them. The goal wasn't to feed the plant more, it was to optimize the conditions under which the plant already grows. Even the orientation of the spiral mattered. Some experimenters aligned it with the Earth's magnetic field, suggesting that direction could influence how energy flows through the system. Whether every detail was fully understood or not, the underlying idea remained consistent. Use simple materials. Use natural forces, and let biology do the rest. If this worked even partially, it would represent a radically different way of thinking about agriculture. And that's exactly where the story begins to shift, from curiosity to conflict. By the early 20th century, agriculture was on the edge of a transformation, not in the fields, but in factories. In Germany, a breakthrough known as the Haber-Bosch process made it possible to produce synthetic ammonia on an industrial scale. What began as a wartime innovation quickly became something else entirely. A new foundation for global agriculture. Factories in Europe and the United States began producing chemical fertilizers in massive quantities. Within decades, production surged from just over 1 million tons per year to tens of millions. And with scale came affordability. Fertilizer became cheaper, more accessible, easier to apply. For farmers, it looked like a solution, but it also introduced something new, something subtle but powerful: dependence. Instead of relying on compost, natural cycles, or one-time tools, farmers now needed to buy inputs every season. Each year, more fertilizer. More cost, more reliance on external supply. It wasn't just a technological shift, it was a business model, and it scaled perfectly. Because unlike a tool that works once and lasts, fertilizer had to be purchased again and again. The industry grew rapidly. Its success depended not just on results, but on repeat consumption. Now place that next to electroculture, a method that claimed to work using a simple copper wire. No chemicals, no recurring cost. If even a fraction of those claims were true, it presented a problem. Not necessarily a scientific one, but an economic one. At the same time, the narrative around electroculture began to change. Newspapers started using careful language, unverified claims, experimental curiosity, eccentric methods. Agricultural journals once open to unconventional ideas became more selective. Research funding followed a similar path. University scientists dependent on institutional support had little incentive to explore something seen as fringe. Even official investigations like those conducted by the British Electroculture Committee rarely reached the public in full. Not because they were necessarily disproven, but because they never became a priority. And over time, something subtle happened. The conversation didn't end. It simply stopped. Electroculture wasn't openly rejected. It was quietly set aside. And as decades passed, a once promising idea faded into the margins of history, replaced by a system that required constant input, constant production, and constant purchase, which raises a difficult question. When a solution doesn't fit, does the system adapt, or does the solution disappear? By the late 1930s, something had changed. Not in the fields, but in the conversation. Electroculture didn't collapse under a single failed experiment. It wasn't publicly debunked or decisively disproven. Instead, it faded. Quietly. Research papers stopped appearing. Letters to journals went unanswered. Experiments that once drew attention were no longer discussed. In academic circles, the topic became uncomfortable. Not necessarily wrong, but not worth pursuing. For scientists, reputation matters, funding matters, and associating with ideas labeled as fringe carried risk, professional, financial, even social. So most simply moved on. The British Electroculture Committee continued collecting data for years, but much of it remained unpublished, archived, categorized, and largely unseen by the broader scientific community. No official conclusion ever fully closed the case. No definitive statement that it worked everywhere. No clear declaration that it failed. Just silence. Over time, that silence became something else. Absence. New generations of researchers never encountered the idea. Agricultural education moved forward without it. Textbooks evolved, and the concept of electroculture slowly slipped out of view. What remained were fragments, old patents, faded photographs, scattered reports. Enough to suggest something had existed, but not enough to keep it alive. And so, a question lingered not loudly, but persistently. Was this simply an idea ahead of its time, or one that quietly disappeared because it didn't fit the direction the world had chosen? For decades, electroculture existed in a strange place, not fully accepted, but never entirely forgotten. Then, in recent years, something changed. The conversation returned. But this time, it didn't come from old patents or anecdotal reports. It came from large-scale institutional research. Scientists at the Chinese Academy of Agricultural Sciences set out to test a version of the same idea, not in small gardens, but across vast agricultural fields. Their experiment covered approximately 3,600 hectares, an area larger than 6,000 football fields. But instead of fertilizers or pesticides, they used something different: electrical field systems. High-voltage wires were suspended above crops designed to interact with the natural electrical gradient between the sky and the earth, similar in principle to what early electroculture pioneers had proposed, but scaled up with modern engineering. The goal was simple. See what happens when plants are exposed to a controlled electrical environment. The results were difficult to ignore. Across multiple test sites, crop yields increased by nearly 30%. More wheat, more rice, more vegetables. And this wasn't the only change. Pesticide use dropped dramatically in some cases by as much as 70 to 100%. Farmers reported fewer insects, healthier plants, and more consistent growth, even in regions where pest control had previously been a major challenge. These weren't isolated observations. They were measurable, repeatable outcomes across large-scale trials. For the first time in nearly a century, the idea that electrical fields could influence plant growth had re-entered mainstream research, not as speculation, but as data. Of course, this didn't prove that every early claim was accurate, and it didn't mean that a simple copper wire could replicate industrial-scale systems. But it did something important. It reopened the question, because if plants respond to electrical environments, and if those environments can be influenced, then perhaps the early experimenters weren't entirely wrong. Perhaps they were just working with tools too simple for a system that required deeper understanding. And perhaps hidden beneath decades of silence, there was always a signal waiting to be measured. As interest in electroculture returns, one thing becomes critically important. Not all methods are the same, and more importantly, not all of them are safe. At its simplest, electroculture can be completely passive. A copper spiral placed in the soil doesn't require electricity batteries or any external power source. It works, if at all, by interacting with the natural electrical field that already exists between the sky and the ground. There is no current being forced into the plant, no artificial voltage, no hidden energy source, just a conductor quietly doing its job. This type of setup is generally considered safe. It poses no risk of electric shock, no interference with nearby devices, no danger to people, pets, or soil health. But not every approach follows this model. Some modern systems, like those used in large-scale experiments, rely on high-voltage electrical lines suspended above crops. These setups can involve thousands of volts. They are carefully engineered, professionally installed, and monitored under controlled conditions. And they come with real risks. Improper wiring, exposed connections, or incorrect handling can lead to electric shock fire hazards, damage to equipment. Even a small mistake can turn an experiment into a dangerous situation. This is where confusion becomes a problem. A simple copper spiral is not the same as a powered electrical system. Trying to recreate industrial results using improvised high-voltage setups is not only ineffective, it can be extremely dangerous. So the distinction matters. Passive methods aim to work with natural forces. Active systems attempt to control them. And if there's one principle worth remembering, it's this: curiosity should never come at the cost of safety. Understanding the difference is the first step toward exploring the idea responsibly. For all the theory, research, and debate, the simplest way to understand this idea is to test it yourself. A basic electroculture setup doesn't require advanced tools or technical knowledge. Just a few simple materials and attention to detail. Start with a length of bare copper wire, ideally around 14 gauge, about the thickness of a sturdy paperclip. Shape the wire into a loose spiral. The diameter should fall somewhere between 5 to 20 centimeters, with at least 3 full turns. The spacing matters. Don't coil it too tightly. Air and light should be able to pass through. Some people use a wooden stick or dowel to keep the shape even. Once formed, place the spiral into the soil. It should sit about 10 to 15 centimeters deep, with the top end slightly above the surface. Now, here's a detail often overlooked, but frequently emphasized by early experimenters: orientation. The tip of the spiral should face magnetic north. A simple compass is enough to find it. While not all modern studies confirm this step, many practitioners believe alignment with the Earth's natural field improves consistency. Position the spiral about 10 to 20 centimeters away from the base of your plant. Leafy greens, tomatoes, beans, and squash are often used in small-scale tests. To evaluate results, keep everything else the same. Same soil, same watering schedule, same sunlight. Then track changes over time. Measure plant height, observe leaf size, watch for pests or disease, take photos every couple of weeks. At harvest, compare yield and overall health. Some gardeners report noticeable differences: faster growth, fewer pests, stronger plants. Others see little to no change. And that's part of the process, because at this level it's not about proving a global theory. It's about observing what happens in your own soil. Today, modern agriculture produces more food than at any point in human history. But it comes at a cost. Global fertilizer use now exceeds 185 million tons per year. Soil degradation continues to rise, and farmers around the world face increasing pressure from both cost and dependency. At the same time, interest in alternative methods is growing, not just because they promise higher yields, but because they ask a different kind of question. What if productivity doesn't always require more input? What if some of the answers we're searching for have already been discovered, just not fully understood? Electroculture may not be a universal solution. It may not replace modern farming, and it certainly raises more questions than it answers. But it challenges a deeply rooted assumption that growth must always come from adding something external. Because if even part of this idea holds true, if plants can respond to natural electrical forces in meaningful ways, then the way we think about agriculture could begin to shift. Not overnight, not completely, but gradually. And maybe that's the real story here. Not whether a single wire can change everything, but whether we're willing to re-examine what we've already accepted as fact. So here's the question that remains. If the solution was simple, quiet, and already all around us, would we recognize it?